Last time we were taking a look at section 1.1, mathematics and problem solving. We talked about taking a look at problems and doing a number of different maybe processes for how we might solve them. And we had done an example where we had a pattern. We had done a second example where we looked for a similar, or we used a similar case and did the same kind of a thing, examine a related problem. And we're going to take another one today. The first one here that we're going to look at today, number 3, says if a soccer league has 10 teams and each team plays every other team once, how many games will the league manager need to schedule at the start of the season? I gave an example last time of a strategy where it says sometimes it's easier to use fewer examples, right? In this case, fewer teams, and figure out what the pattern is or what process is happening, and then generalize it to more. And that's what we're going to use on this one. We're going to examine a simpler case. So the case we're going to examine is what would have happened if we only had 3 teams. 2 teams is like, what do they usually call it? It's a trivial case. That's what I want. It's a trivial case, right? If it's just 2 teams, they only schedule 1 game and we're done. And that doesn't give us any useful information. Okay, so we're going to start with 3 teams and see what happens. See what happens, yes. And just for abbreviations, let's call the teams A, B, and see how we would pair them up to have a game. So we could have teams A and B play each other for a game, right? What else could we have? A and C. What else? B and C. And if you're not careful, what you might think is that you can also have B and A, C and A, and C and B. Why do we really not need those? Any idea? It's the same teams, right? We've just repeated the information in the other order. And sometimes, there are leagues where you would play, your court and we play at my court and something like that. So that might be a useful fact at some point. But in this case, they're only going to play each other 1 time. So we don't really need these 3. So how many we had 3 teams. How many games are we going to actually schedule if we only have 3 teams? Just 3 games. Now, part of the reason I wanted to write down all 6 of them originally, though, is so that we can examine what happens to those duplicates. Because once I introduce a 4th team, it becomes a lot more combinations of things to write down very quickly. It's fast. It's going to just explode on us. So what is happening? Well, I started out with 3 here, right? 6 here. These would be called actually combinations. If you've had any number theory in the past, you might have seen that word. There are 6 combinations. Why was it 6 combinations when I had 3 teams? Any guesses?
So it's all the different ways you can put those together.
So if I just told you 10, can you speculate what would happen for 10 when I got from 3 to 6? Multiply it by 2. So do you think that if I do 10, I would just multiply by 2? Not quite. So why would it be times 2? Any ideas? Let's think like this. If there's 3 teams, how many games is each team playing? 2. Right? That's where the 2 is coming from. Each team, and there are 3 teams, plays 2 games. And if you did 3 times 2, you would get the 6, right? But if we really do 3 times 2, we've counted every game twice. We counted it when we counted all the teams that games that A played, and we counted it when we counted all the teams that B played. So we have double counting going on. So what we really have going on here is we have our number of teams, that was 3, times their number of games, and then what did we have to do? What did we have to do to get the 3? Divide by 2, because I double count every single one of them when I do that. And the same thing will happen whether I have 2 teams, or 4 teams, or 10 teams. So we can use that model We can take a look at where those numbers came from. Why did I get 6? Well, I got 6 really because it was 3 times 2. 3 teams, 2 games each. And then I divided by 2 because I double counted everything. So if I have 10 teams, what's going to happen?
Each team plays 9 games.
They do. I have 10 teams. Each team plays 9 games. But if I were to write all those combinations out, there'd be twice as many as I need, right? I'd have an AB and a BA. I'd have an AC and a CA, all the way down the line. So what do I have to do with the 10 and the 9? I would divide their result by 2. So what is 10 times 9? 90. And then divided by 2 would be 45. So there are 45 total games. Now, there are times, and I know you've experienced it, where there's these sort of examples created that are so out there, like they're not really an example. They're just a way to get you to do some math, but they don't really have any practical application. Why would you, practically speaking, want to know that there's 45 games?
See how many refs you have to hire.
Refs you have to hire, fields you have to reserve spaces for. Make sense? Okay, so there's an actual, and this is a really good example of one where there's a super practical application of this. A similar example that uses the same process but doesn't have that practical application is this. If there are 10 people in the room and everybody shakes hands with every other person in the room, how many total handshakes are there? Like, who cares, right? It's the exact same problem, but that's not real practical. It just doesn't matter how many handshakes there are. But this actually makes sense. This is a real life problem that you would have to do if you were scheduling the refs, if you were scheduling the fields, if you were scheduling all of it. So, all right, let's take a look at another one. A store sells bicycles and tricycles. There are a total of 15 cycles in the store, and there are 35 wheels on those cycles. How many of each type of cycle are there in the store? So some of you probably looked at this, and as I was reading it, you thought, I need an X and a Y, and I need to do 2 equations and try to figure out how to eliminate something or substitute something in or something of this nature. My daughter is in Algebra 1 in 8th grade right now, and they're doing this. This would be an example of something she'd see in her textbook. And you can do it. There's nothing wrong with doing it that way. But I contend that you can do it at a much simpler level with younger kids. So I want to show you an example of that, okay? This one actually is a really good one for making a diagram. In your mind, you know what a bicycle and a tricycle look like. What's the difference? 2 wheels and 3 wheels. Now, we talked last time, and I think there were 2 people in here who said, I draw pretty well, and the rest of you just didn't put your hands up. That's what I remember. Maybe I'm remembering my other class, I don't know. But I don't draw very well. So I'm going to show you my version of a bicycle. Are you ready for this? You ready? This is my bicycle. There you go. By definition, that's my bicycle. All right, so we know that we have how many cycles total? 15. So the fewest number of wheels that I could have then is what? 30. I could draw this image 15 times and I would have 30 wheels. That's what I want you to do first, okay? And I have an advantage because I have copy paste. But it probably will still take me longer than you. Okay, I have 15 cycles now. And you guys already told me that that's 30 wheels. But the problem gave me slightly different information. How many wheels am I supposed to have on all these cycles? I'm supposed to have 35, so how many wheels short am I? 5. So what am I going to have to do to my picture to make it match the information in the problem? But if I add a bicycle and a tricycle, I won't have 15 cycles. What else could I do?
Add some wheels to some of the other
So I could, in essence, on my paper, turn the bicycles into tricycles, right? Yeah, I can add a wheel. How many cycles need a wheel added? 5, because that's the 5 missing wheels. So, as creative as I am, this is how I do that. Look at this. Look at that. It's a tricycle, right? Okay, there's 3, 4, and 5. The question is, does my diagram match the information? Do I have 15 cycles? Yes. Do I have 35 wheels? Yes. Did I write X and Y anywhere? I didn't. But a picture tells me exactly what I've got, right? What's the answer to the question? 5 tricycles and 10 bicycles. It's clever, right? It's pretty straightforward, but it's probably not what you thought of. And you know why? Because you've had more math to think of it differently. But this is an example of how you could do this problem with a diagram. All right, we're going to do an example of the guess and check strategy. It's going to have a diagram in it, and it's going to have a table. So it says guess and check, but we're actually going to be using kind of 3 strategies at once to keep our organization of our thoughts. It says we have 48 feet of fencing, and we wish to make an enclosure along one side of an existing barn. What lengths would the sides need to be to have the greatest area enclosed for our chickens? Okay. This is a pretty practical application. If you have only so much money to buy the fencing and that's all the fencing you've got, what's your best bang for your buck? That's the question. So the first thing I'm going to do is I am going to use the drawing tools to create this image. I have a barn. So here's my barn. And I'm going to make an enclosure along the side of the barn. So when I draw my enclosure, how many sides are there going to actually be that are fencing? 3. Think about your house if you do have a fence or fences that you've seen. People don't fence along the side of the house, right? That would be a waste of the resources, agreed? So we only have 3 sides to our fence, okay? Now, how are you legitimately going to draw your fence? What shape is it going to be in? Square or rectangle, right? It's going to be 3 sides, the space inside, and it might end up being a square, but at the very least it's a rectangular shape. We're not going to make a circle or a semicircle out of the fence, right? It's just not practical for what we're talking about. So here's my fence. So ignoring everything in the problem itself, just with the shape that I've drawn, tell me something you know about this shape. There's several things I know you know.
2 of the sides have to be the same.
2 of the sides have to be the same. At least 2 of the gray sides, right? The top one and the bottom one. So whatever these are, and we'll give it letters just so I can talk about it. I think we probably could call that the width. So we'll call it W. And it has to be the same as this one. So if one of them's 5, the other one's 5. Does the third side have to be the same? It didn't have to be. Now, some of you mentioned it could be a square, and it could be the same, so it's a possibility, but it doesn't have to be. So for now, let me call it L to represent that it could be something different. Now, the problem asks us to maximize what? The area. What's the area of this shape? How do you find the area of this shape? Length times width, right. So we multiply those dimensions together. So if I decide that the width is 5, that's going to force the length to be a certain amount because I have 48 feet of fencing. And then I could use those dimensions to find the area. So I'm going to do that example since I just mentioned 5. I don't even know why I said 5, but we're going to use it. And we're going to create a table to help represent it so that we can keep our guesses straight. Guess and check is only a useful strategy if you keep track of your guesses. Otherwise, you're going to be guessing an awful lot and maybe not very effectively. So there are some things that this particular problem has that we need to be careful of. We have the width, we have the length, we have the area, and we have to make sure that whatever the width is, plus itself again, because there's two widths, plus the length, adds up to what? Not the area, the what?
48.
The 48. If it only added up to 45, well then we could have made it bigger because I have 48 feet of fencing. I'd have been wasting some of my fence, right? Okay, so we're going to now guess and check. I gave a guess of 5 a minute ago, and so I'm going to write it down. It's a terrible guess, by the way, but we're going to still write it down just so I can show you the process of how it would work. If the width is 5, then it means that I have a 5 here and a 5 here, right? That's 10 feet that I've used up. How many feet are left over? 38. So I would have a 38 here. And then what would I do to find the area? I'd multiply them together. So grab a calculator. I hope you brought one today. If not, then just sit tight and somebody will have a calculator. If not, I've got one. I hear lots of movement, so I do think we have some calculators too. That's good. What is 5 times 38? 190. And I don't have any units on this, so if you want to leave units off for the time being, that's fine. In the end, when we give our answer, we need to make sure we have units. But sometimes it gets just messy in the side of a table when we keep writing the same thing over and over again. So it's okay if you leave it off for now. All right, I need somebody to improve upon my guess because I'm going to tell you it was a terrible guess. What could I do instead? Give me a different width. We're going to keep choosing width every time. 12. All right, so if I have a 12 here, that means I have 12 here and here. How much of my fencing is then used up? 24. So how much would be left? 24, right? Okay, so my second value in my table, my length would be 24. If I had 12 and 24 of my as my length and my width, what's my area? 288. Is that better than I had before? It's a lot better. It's a lot more space. Now you might be thinking, well, why should that be the case? So imagine you've got to spread this fencing out, right? And you've basically created, the first one I created was this really long, skinny chicken run. That's what it really is, right? And instead, you've made the dimensions so it looks more like this. Can you see that there's more space inside that sort of square-ish shape than that long rectangle shape? Yeah, that makes sense, right? So the long, skinny thing's not going to have a lot of area. So it makes more sense that the length and the width should be sort of closer together than 5 and 38 were. Are you guys with me? All right, so it's better than it was before, but is it the best? How will I know? I got to guess a few more times at least, right? Maybe it is, maybe it isn't. It's certainly better than the 5, but it may not be the best. So what would you like to guess instead? Different width. 16. Okay, so let's put a 16 here. Whoops. 16. So I've got 16 here and here. How much have I used up? 32. So how much is left over? 16? All right. So let's put a 16 here. What happens when I multiply 16 times 16? 256. So it's not more, but at least helps us to get a better idea of whether, which one's closer. Was it 256? Okay, so one of the things that tells us already is I don't need to pick anything bigger than 16. Do you agree? Somewhere in between these, it started going down. Or maybe even somewhere before the 12, but it's going down right now. So picking a number bigger than 16 is not going to be helpful. I still don't know if the 12 and 24 are the best choice, so let's guess something else. 14. Okay, 14 and 14 are what? 28, leaving me with 20. How much area does this enclosure have? 280 is right. So is that bigger or is it smaller than my other values? It's smaller than the 288. So again, I wouldn't need necessarily to test 15 now. It would be useless information, right? Because I know that 14 was less and 16 was less, so 15 is also going to be less than my 288. What else might I want to test? I can test 13. 13 and 13 would give me 26. Good job. And that leaves me with how much? 22. 13 times 22. 286. So how am I doing on my guessing? I'm getting closer, right? The 286 is closer. So we're sticking with whole values because we're still working along the lines of children, young children. These problems are not going to have decimals. So in theory, could you use a decimal in the problem? Well, yes, in theory you could, but let's remember we're in the number theory class where the highest we're going in terms of numerical values or types of numbers is integers. So we're not doing any fractions or decimals in this class. We don't need to worry about that. Now, I still don't know what happened between 5 and 12 though, right? Could there be a value between 5 and 12 that might actually be bigger? Well, maybe. So I need to test something and see what happens. So what number might we like to test? 11 would be a good choice because if you take a look, that 286 was pretty close to the 288, right? So let's try 11 and see what happens. 11 and 11 for my width will give me what for my length? 26. And what is 11 times 26? 286. And that would be smaller than the largest number on my table, right? It's not bigger. Do I need to go down to 10 or 9? I don't. I'm already trending downward on the other side of the number 12, right? So we had the answer quite a bit ago, but we had no way to know for sure that it was until we keep working through some more guesses. Does that make sense? So this one is, in fact, our best, in this case, biggest area. We need to make sure we answer the question as it was asked. It says, what lengths would the sides need to be to have the greatest area? So what are the answers, or what is the answer to the actual question asked? 12, was it feet, right? So let's make sure we get units on it now. 12 feet, 12 feet, and 24 feet. And in whatever order you want to list those out. Now the question might not have asked this. It could have said, what's the greatest area you could choose, right? And if it were asking you that, what would the answer be? 288, and then what would the units be? Square feet. Looks like feet with a little squared on the outside of it. Square feet. So we need to make sure we're being really careful for the question that's asked and using units when they are a part of the problem presented. Any question about this one? All right. This is a lovely example of working backwards. I think it's a fun one. It says, one winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. What was the temperature at midnight? All right, so what do you think we should do?
Start with a 32.
Start with where we actually ended the question, right? The 32. And it might be a good idea to kind of write the numbers in order of their time sequence. So what is the earliest time it references? There's a time before 5. Midnight actually would have come first, right? So midnight is first. And then I think you guys said 5 a.m. Then what? 9 a.m. And then noon. And Eric is right. We have that 32 as our ending value at noon. So at noon it was 32 degrees. It was freezing. Must be winter, right? Because I'm guessing this is a Fahrenheit scale. That's what it seems like, right? Okay. So let's see. It says it ends at 32. And what we're going to do is we're going to work our way backwards to try to figure out what was it at midnight. So what would I do to get from noon, simply one step, if you will, backwards to the 9 a.m. time? Subtract 10. Why would I want to take this going backwards and subtract 10? Because it said between 9 and noon it had risen 10 degrees. So if I'm going to backwards, I would subtract 10 degrees. So what temperature was it at 9 a.m.? It was 22 degrees. All right, we're going to keep this process up. What would I have to do to go back to 5 a.m.? Divide by 2. It says that by 9 a.m. the temperature's numerical value had doubled. So doubled means it was originally multiplied by 2. So we're going to divide it by 2, which would give me 11 degrees. I'd like to make a comment. This question is straight out of your book, except for the condition that I changed the phrase where it says the temperature's numerical value. It just says in your book the temperature. And you might be thinking like, well, what's the difference? Well, because if you double 11 degrees Celsius and you double 11 degrees Fahrenheit's numbers, those will not end you up at the same temperature because the scales are different. So temperature is one of those weird things. I mean, like I can double my distance running and it doesn't matter if I'm in feet or meters. But Celsius and Fahrenheit don't work that way because 1 degree increase in one is not the same as 1 degree increase in the other one. You guys following with me? So it's sort of maybe a nuance to what's being said, and your book might do it wrong. Just letting you know, though, that mathematically it doesn't make sense to say the temperature doubled because it depends on the scale you're talking about. All right, so let's go on. My goal is to get to midnight. What do I have to do to get back to midnight? Yeah, I have to do something with the 15. Now, originally it said that it fell by 15 degrees between midnight and 5 a.m. So falling by 15 degrees would mean that it subtracted 15 degrees. This one was a 10 before. It added 10 to get from 9 to noon. It multiplied by 2 to get from 5 to 9. It subtracted 15 to get from midnight to 5. So what are we going to do? We're going to add 15. So if we add 15 to the 11, we get 26 degrees. Now, we'll just report it the way that they have. It's just 26 degrees. Of course, we recognize that it's probably Fahrenheit because that's what, well, honestly, it's the only thing that really makes sense in the context. So, all right. Last thing for today. I want to talk to you about an example that shows up in your group work that you're going to do. It talks about the 12 days of Christmas. And you probably know the 12 days of Christmas, but depending on which song you go with or storybook you look at, sometimes they switch some of the items on the days up, like the 12 drummers drumming might be 10 drummers drumming. I don't know if you've ever experienced this before, but we have a children's book who does it wrong according to the way I sing it, okay? So I want to make sure that everybody's using the same days on the days of Christmas. There's actually religious symbolism for the 12 days of Christmas as well. I want to present that for you because I think it's kind of cool. The first day of Christmas, which is a what? I didn't write this one down. What do you get on the first day of Christmas in the song? Partridge in a pear tree. So on the first day of Christmas, the 1 represents true love, which is God. Second day of Christmas is turtle doves. That represents the Old and the New Testament, too. The 3 French hens represent faith, hope, and love. The 4 calling birds are your 4 Gospels, Matthew, Mark, Luke, and John. The 5 golden rings are the Pentateuch. Do you guys know what the Pentateuch is? First 5 books of the Old Testament. Very good. So that would be Genesis, Exodus, Leviticus, Numbers, Deuteronomy, the real exciting ones that we all love to read, right? They're a little bit more difficult to make through than the 4 Gospels for me. The 6 is 6 geese a-laying. That's the 6 days of creation. 7 is 7 swans a swimming, the 7 gifts of the Holy Spirit. 8 is 8 mates of milking, which is the 8 Beatitudes. 9 ladies dancing, 9 fruits of the Holy Spirit. I should give extra credit if you could write all these things down. That would be actually a good activity. Maybe next time. 10 Lords a leaping is the 10 Commandments. Do you know the 10 Commandments? I usually end up forgetting one of them when I start going through them. The 11 pipers piping is the 11 faithful apostles. So we're excluding Judas. Good. 12 drummers drumming is the 12 points of the doctrine and the Apostles' Creed. All right, so we have 15 minutes, which is perfect for starting group work. So I need to put you guys in groups. And this will be due then on Friday.